Hello and welcome. In this video, we will explore two key topics in differentiation that are essential for the IB mathematics analysis and approaches higher-level curriculum. First, we will learn how to differentiate inverse trigonometric functions. Second, we will delve into the concept of higher-order derivatives. By the end of this session, you will be able to apply the chain rule and product rule to differentiate complex functions involving inverse trigonometric functions, and you will be able to find and interpret second and higher derivatives. Let's begin with our first topic, differentiating inverse trigonometric functions. These functions, like arcsin, arcos, and arctan, are the inverses of the standard trigonometric functions. You are expected to know the derivatives of these functions. Let's list them out. The derivative of arcsin of x is 1 over the square root of 1 minus x squared. The derivative of arcos of x is the negative of that, negative 1 over the square root of 1 minus x squared. And the derivative of arctan of x is 1 over 1 plus x squared. These are the fundamental formulas. However, in IB problems, you will often encounter compositions of these functions, requiring the use of the chain rule. The chain rule states that the derivative of a composite function f of g of x is the derivative of the outer function, f prime, evaluated at the inner function g of x, multiplied by the derivative of the inner function, g prime of x. Let's see how this applies to inverse trigonometric functions. If we have arcsin of u, where u is a function of x, its derivative is 1 over the square root of 1 minus u squared, times the derivative of u with respect to x. Similarly, for arcos of u, the derivative is negative 1 over the square root of 1 minus u squared times du d, and for arctan of u, the derivative is 1 over 1 plus u squared times du dx. These are the general forms you should use. Let's work through some examples. Let's start with a straightforward application of the chain rule. Consider the function y equals arctan of 3x. Here, our inner function, u, is 3x. The derivative of u with respect to x is 3. So u equals 3x and du dx equals 3. Using the chain rule for arctan, we have di dex equals 1 over 1 plus u squared times du dx. Now we substitute our expressions for u and du dx. This gives us 1 over 1 plus the quantity 3x squared, all multiplied by 3. Simplifying the denominator, 3x squared is 9x squared. So our final answer is 3 over 1 plus 9x squared. This example demonstrates the direct application of the chain rule to an inverse trigonometric function. Now let's look at a more complex example that combines the product rule with the chain rule. Let's find the derivative of y equals x times arcsin of x. Notice that this function is a product of two functions, x and arcsin of x. Therefore, we must use the product rule. The product rule states that the derivative of u times v is u prime v plus u v prime. Let's define our u and v. Let u equal x and v equal arcsin of x. Now we need to find their derivatives, u prime and v prime. The derivative of u prime is simply 1. The derivative of v prime is 1 over the square root of 1 minus x squared. Now we can substitute these into the product rule formula. Di slash a dx equals u prime times v, which is 1 times arcsin x, plus u times v prime, which is x times 1 over the square root of 1 minus x squared. Simplifying this expression gives us our final answer. The derivative is arcsin of x plus x over the square root of 1 minus x squared. This example shows how to combine the product rule with the differentiation of inverse trigonometric functions. Let's tackle another example, this time involving the quotient rule. Find the derivative of y equals e to the power of x divided by arcos of x. Since this is a quotient, we must use the quotient rule. The quotient rule states that the derivative of u over v is u prime v minus u v prime, all divided by v squared. Let's identify u and v. Let u be the numerator, e to the x, and v be the denominator, arcos of x. Now we find their derivatives. The derivative of u prime is e to the x. The derivative of v prime is negative 1 over the square root of 1 minus x squared. Substitute these into the quotient rule formula. D dex equals u prime v minus u v prime, all over v squared. Let's simplify the numerator by factoring out e to the x. This gives us e to the x times the quantity arcos x plus 1 over the square root of 1 minus x squared, all divided by arcos x squared. This example shows how to apply the quotient rule when one of the functions is an inverse trigonometric function. Now, let's move on to our second main topic, higher-order derivatives. A higher-order derivative is simply the result of differentiating a function multiple times. We are already familiar with the first derivative, which we denote as f(a)(c) prime of x y prime or d(i)(c). The first derivative, f prime of x, represents the instantaneous rate of change of the function f of x. The second derivative is the derivative of the first derivative. In other words, it's the rate of change of the rate of change. We denote the second derivative as f double prime of x y double prime, or d squared y over dx squared. The notation d squared y over dx squared can be thought of as applying the derivative operator d(dx) twice to y. So d squared y over dx squared is equivalent to dx of di. We can continue this process to find the third derivative, the fourth derivative, and so on. The third derivative is f triple prime of x or d cubed y over dx cubed. For the fourth derivative and beyond, we use parentheses to denote the order, like f superscript 4 of x or d to the power of 4y over dx to the power of 4. Let's work through an example to see how to calculate a second derivative. Let's find the second derivative of a polynomial function. Find the second derivative of f of x equals 2x cubed minus 3x squared minus x plus 5. To find the second derivative, we must first find the first derivative. Using the power rule, the derivative of 2x cubed is 6x squared. The derivative of 3x squared is 6x, and the derivative of x is 1. The derivative of the constant 5 is z. Now, to find the second derivative, we differentiate the first derivative, f prime of x. So f double prime of x is the derivative of 6x squared minus 6x minus 1. Applying the power rule again, the derivative of 6 squared is 12x, and the derivative of 6x is 6. The derivative of the constant 1 is 0. So the second derivative of f of x is 12x minus 6. This process is straightforward for polynomials. Let's try an example that requires the product rule for the first derivative. Find the second derivative of f of x equals x times cosine of x. First, we find the first derivative using the product rule. Let u equal x and v equal cos x. Then u prime is 1 and v prime is negative sin x. Applying the product rule, p prime of x is 1 times cos x plus x times negative sin x, which simplifies to cos x minus x sin x. Now we need to differentiate this result to find the second derivative. Notice that the second term, x sin x, is another product. So f double prime of x is the derivative of cos x minus the derivative of x sin x. The derivative of cos x is negative sin x. For the second term, we apply the product rule again. Let u equal x and v equal sin x. Then u prime is 1 and v prime is cos x. The derivative of x sin x is 1 times sin x plus x times cos x, which is sin x plus x cos x. Now we substitute this back into our expression for f double prime of x. F double prime of x is negative sin x minus the quantity sin x plus x cos x. Distributing the negative sign and combining like terms gives us our final answer. F double prime of x equals negative 2 sin x minus x equals. This example highlights that finding higher derivatives can sometimes require repeated application of differentiation rules. Let's look at an example involving the chain rule for the first derivative. Find the second derivative of y equals e to the power of 3x. First, we find the first derivative using the chain rule. The derivative of e to the u is e to the u times du x. Here u is 3x, so dux is 3. dx equals e to the u times duc e, which is e to the 3x times 3, simplified to 3e to the 3x. So the first derivative is 3e to the 3x. Now we differentiate this to find the second derivative. d squared I over dx squared is the derivative of 3e to the 3x. The constant 3 can be pulled out of the derivative. This becomes 3 times the derivative of e to the 3x. We just found that the derivative of e to the 3x is 3e to the 3x. So we have 3 times 3e to the 3x, which equals 9e to the 3x. Notice a pattern here. The first derivative was 3 times the original function, and the second derivative was 9 times the original function. This pattern continues for higher derivatives. Let's explore that pattern further with a proof by mathematical induction, a common technique in IB higher level. Suppose y equals a times e to the bx, where a and b are constants. We want to prove that the nth derivative is b to the n times y. Step 1, base case. We need to show the formula holds for n equals 1. The first derivative, di sui x, is a times b times e to the bx. This can be written as b times the quantity a e to the bx, which is b times y. So the formula holds for n equals 1. Step 2, inductive hypothesis. We assume the formula is true for some positive integer k. We assume that the kth derivative is b to the k times y. Step 3, inductive step. We must prove the formula is true for n equals k plus 1. The k plus 1th derivative is the derivative of the kth derivative. Using our hypothesis, this is the derivative of b to the k times y. Since b to the k is a constant, we can pull it out. This equals b to the k times di dx. We know from our base case that di dx is bi. Substituting this in, we get b to the k times bi, which simplifies to b to the k plus 1 times y. This is exactly what we needed to prove. Step 4, conclusion. By the principle of mathematical induction, the formula is true for all positive integers n. Therefore, we have proven that the nth derivative of y equals a e to the bk is b to the n times y. Let's look at another common type of problem, verifying a differential equation. If y equals sin of 2x plus 3, show that the second derivative plus 4y equals 0. To do this, we need to find the first and second derivatives of y. Using the chain rule, the first derivative, di slash dx, is 2 times cos of 2x plus 3. Now we differentiate this to find the second derivative. The second derivative, d squared y over dx squared, is the derivative of 2 cos of 2x plus 3. Using the chain rule again, this is 2 times negative sin of 2x plus 3 times 2, which simplifies to negative 4 sin of 2x plus 3. Now we substitute our expressions for y and d squared y over dx squared into the given equation. We need to check if negative 4 sin of 2x plus 3 plus 4 times sin of 2x plus 3 equals 0. The two terms are identical but with opposite signs, so they cancel out. This gives us u equals 0, which is true. Therefore, we have shown that the equation holds. Let's conclude with a final example that combines several concepts. Given f of x equals x over x squared plus 2, find the value of x for which the second derivative is 0. First, we find the first derivative using the quotient rule. Let u equal x and v equal x squared plus 2. Then u prime is 1 and v prime is 2x. Applying the quotient rule, prime of x is 2 minus x squared, all over the quantity x squared plus 2 squared. Now we find the second derivative, f double prime of x, by differentiating f prime of x. This requires the quotient rule again. Let u equal 2 minus x squared and v equal x squared plus 2 squared. Then u prime is negative 2x and v prime is 4x times x squared plus 2. Applying the quotient rule, f double prime of x is negative 2x times x squared plus 2 plus 4x times x squared minus 2, all over x squared plus 2 to the power of 4. We can simplify this by factoring out a common term from the numerator. Factoring out negative 2x times x squared plus 2, we get negative 2x times x squared minus 6, all over x squared plus 2 cubed. Now we need to find x such that f double prime of x equals 0. This means we set the numerator equal to 0. Negative 2x times 6 minus x squared equals 0. This equation is true if x equals 0, or if 6 minus x squared equals 0. Solving 6 minus x squared equals 0 gives x squared equals 6. So x equals plus or minus the square root of 6. So the second derivative is 0 at x equals 0, x equals the square root of 6, and x equals negative the square root of 6. Let's quickly recap what we've covered. We started by learning the derivatives of inverse trigonometric functions and how to apply the chain, product, and quotient rules to them. We then moved on to higher-order derivatives, understanding that the second derivative is the derivative of the first, and so on. We saw how to calculate these derivatives and even proved a general formula using mathematical induction. You are now equipped to solve a wide range of differentiation problems at the IB higher level. The key is to identify the correct rule to apply at each step. To solidify your understanding, here are 5 practice questions in the style of IB assessment. Pause the video, work through them, and then check your solutions. Question 1. Find the derivative of y equals e to the x times arctan of x. Question 2. Find the second derivative of f of x equals x squared times ln of x. Question 3. If y equals arcos of x over 2, show that the quantity 4 minus x squared times the second derivative minus x times the first derivative equals 0. Question 4. Find the third derivative of g of x equals cos of 3x. Question 5. Let f of x equals e to the negative x times x plus 2. Conjecture a formula for the nth derivative, f superscript n of x, and prove it by mathematical induction. Welcome back. Let's go through the solutions to the practice questions. For question 1, we use the product rule. The derivative is e to the x times the quantity arctan x plus 1 over 1 plus x squared. For question 2, we find the first derivative using the product rule, which is 2x ln x plus x. Then we differentiate again, using the product rule on the first term, to get the second derivative, 2 ln x plus 3. For question 3, we find the first and second derivatives using the chain rule. Substituting them into the equation gives us 0 equals 0, thus proving the statement. For question 4, we differentiate 3 times using the chain rule. The third derivative is 7 sin of 3x. For question 5, by finding the first few derivatives, we can conjecture that the nth derivative is negative 1 to the n times e to the negative x times the quantity x plus 2 minus n. This can then be proven by induction. I hope these examples and practice questions have helped you master the differentiation of inverse trigonometric functions and higher-order derivatives. Thank you for watching. Before we finish, let's quickly address a few other problems from the textbook that are worth noting. Problem 8 asks for the derivative of arcsin x plus arccos x. The derivative of arcsin x is 1 over the square root of 1 minus x squared, and the derivative of arccos x is negative 1 over the square root of 1 minus x squared. Adding them together gives 0. This is because arcsin x plus arccos x is a constant pi over 2. Problem 9 asks you to prove the general chain rule formulas for inverse trigonometric functions. For example, to prove the derivative of arcsin of x over a, you can use the chain rule with u equals x over a. This gives 1 over the square root of 1 minus x over a squared times 1 over a. Simplifying the denominator leads to the desired result. Finally, problem 18 is a theoretical question about the derivatives of even and odd functions. If f is an even function, its derivative f prime is odd. If f prime is odd, its derivative f double prime is even. This pattern continues. So the nth derivative is even if n is even, and odd if n is odd.